Thank you very much. So this is joint work with Benjamin Aminof, Aniello Murano, and Sasha Rubin. So in planning, we have the characteristic of modeling the dynamic environment in which the agent acts in, okay? And this model is essentially the knowledge that the agent has about its environment. So the agent assumes this knowledge, assumes that the environment works in a certain way, and exploits such assumption in order to derive this, when it derives its plan. And we have many examples of this kind of assumption, this kind of specification of the environment. So, for example, FS specification, domains, fairness, other form of constraints, for example, coming from generalist planning, like here, always, eventually, if I do the action decrease, eventually I will get to 0. Now, all of these specification can be expressed in LTL, all of them, okay? But can we say that every LTL formula can be used as an environment specification? So essentially, of all this formalism, I can write them in logic in LTL, but then my question is any LTL formula good as an environment specification? And the answer is no, it is not the case. For example, if I have something like eventually do decrement. You see, this is not something about the environment. This is something about the agent. It's the agent that does the action, not the environment. So not every logical specification is actually an environment specification. So I will need to come back to this point. Now, how we do planning in this setting, if we want to consider instead of a domain, we want to consider to have a formula as our environment specification. Often, we think that what we need to do is to actually synthesize a plan for an implication. Okay, so the implication is, if you satisfy the environment, then you need to satisfy the goal. So if the environment are satisfied, then you need to satisfy the goal. Now, this implication is actually very tricky, because let's see what he said in a precise way. So he says, all the traces that satisfy the environment, so the specification of the environment, they need to satisfy also the goal. But this is a little bit unsatisfactory, because the traces are not about the environment. The traces are about the play, the simultaneous play of the environment and the agent doing the action. So the traces will not be generated if the action were not there. So this specification, in this sense, it's a little bit unsatisfactory, because we essentially don't know what we are assuming of the environment. So in this paper, we actually propose to see environment specification as specification of strategies. Okay, so let me tell you what are strategies. So strategies are, sometimes we call it also policy, okay? But they are not stateless policy, they are stateful policy, in the sense that they consider the entire history so far, in general, they consider the entire history so far, and then they determine the next action in the case of the agent, or the next effect in the case of the environment. So an environment specification, by the way, let me tell you, notice that this shape of strategies is the standard shape of any kind of process. Any kind of computable process has this characteristic. It sees the history and decides what to do next. Okay, any program is like this. So this is a very general way of seeing the behavior of dynamic systems. Okay, so the environment specification is then a specification of this kind of strategies, environment strategies. Now I need to tell you that if you give me an environment strategy and if you give me an agent strategy, the two things together combined will generate one trace. Okay, this is the so-called the play, the trace that is generated by the simultaneous execution of the two strategies. And with this notion of trace, now I can tell you very clearly what is planning under environment specification. Essentially, for all the strategies that satisfy the environment, remember now the environment is a set of strategies. So for all the strategies that are in the good set of strategies, the ones selected by the environment, then the traces generated by the agent strategy, the chosen agent strategy, and the environment strategy go to the goal, okay, satisfies the goal. So essentially our task is find the strategy for the agent such that this little formula is true. Now, let's go back to when we can consider an environment strategy a legitimate environment specification. Sorry, when we consider an environment specification legitimate. Actually, in this setting, it's very easy. An environment specification is legitimate if it is consistent. And what it means consistent? Well, like in logic always, consistent means non-empty. Okay, so you want this set env of strategy to be non-empty. Okay. Now let's switch back to LTL. So till now I have not talked about LTL, I've talked about a completely general setting. I was talking about set of strategies, a very general problem, very general formulation. Now I want to go back to LTL. And my question is, but can I use LTL to specify environment strategies? Well, yes and no. So first of all, no directly, because LTL specifies traces, not strategies. So strategies are trees, not traces. But indirectly, yes, through the notion of realizability. So there exists a strategy that forces the formula to be true. What it means forces the formula to be true? That it will make the formula true notwithstanding what the strategy of the opponent will do. Now we can define when an agent strategy realizes a certain formula, when an environment strategy realizes a certain formula, and as you see, it simply means that the trace generated against every strategy of the environment, every strategy of the agent will satisfy the formula. And I'm going to use this little notation to be read: strategy forces phi. Okay? And now I can give you everything in LTL. So the semantics of the environment specification are all those strategies such that the strategy forces the environment to be true, makes the environment true. It's a winning strategy for the environment. When the environment specification is consistent if it's not empty, if there exists at least one strategy that satisfies the environment and that forces the environment. Now, environment is an LTL formula. So what it means that we can solve this through LTL synthesis, and we know that this is a 2x time complete problem. We have techniques for solving it. Finally, let me go back to planning for a goal under environment specification. What it is this? Now is for every strategy that satisfies the specification, that forces the formula n to become true, the traces generated by my chosen strategy as an agent will, together with any of these strategies, will make the goal true. Okay, remember here goal is also LTL, it's not reachability simply. Okay, so all the definitions are fine. Now, how we solve it? Well, we have a first theorem that says the following. If I have an environment specification and a goal, then if I find a strategy for the agent that satisfies the implication, the one that I showed in the first slide, then that strategy also realizes the goal in the environment specification, so satisfy also solves the planning problem we are interested in. However, the converse is not true. Okay, so somehow this implication is a little bit stronger than needed. Okay, so they are not equivalent. I'm going to skip this. I think I don't think I need to. How am I with time? 7 minutes. So I can actually do it. So let me give you a little example that shows how to do it. So let me show a case in which this converse fails. We have F that is controlled by the environment. It's a proposition controlled by the environment. And A and B that are controlled by the agent. Oh, sorry, I'm missing the formulas here. I'm sorry, I'm missing the formula. So the formula would be F implies A and F implies B. Okay? And F implies A is the specification of the environment, and F implies B is the goal. Sorry, I somehow deleted in reducing the slide. So now, is this a consistent, so is F implies A consistent environment specification? Yes, because you can do not F, and this is under the control of the agent. And now if you do not F, obviously reaching, so the satisfaction of F implies B for the goal, it is immediate because the premise of the implication is false. So we have that in this case, every strategy for the agent would satisfy the goal, okay? But instead, if we look at single traces, one trace at a time, this is not the case. And so what we have is that the implication is not satisfied. Okay, so this strategy satisfies the planning problem, but not this implication. Okay, this is a bad news because it means if it is an implication, we know how to do it. Instead, now we don't really know how to do it. However, there is another little theorem that actually gives us the solution. And this theorem says the following. While planning under environment specification is different from solving this implication, they are equally realizable. What it means? It means that if there exists a strategy for the agent that satisfies planning under the environment specification, then there is another strategy for the agent that satisfy the implication. And since all the strategies satisfy the implication, they satisfy also the problem, so we are done. Okay. So what it means that now we can solve LTL synthesis. We can solve planning under environment specification via LTL synthesis in 2x time. The last thing I want to do, and in the paper you will see many results along this line, is actually to get a little bit deeper in this process of planning. And in particular, I want to start considering separating the contribution of environment specification. In particular, what I want to do, I want to separate the domain from further assumption. Okay? So I want to separate the domain for further assumption. Why? Because the domain is big. Assumptions often are small formulas. So if I can separate them, my complexity, my analysis will be much more precise. And obviously I want to separate also for the goal. So the first thing, by doing this separation, what I get that checking that an environment specification formed by a domain and an additional assumption is actually consistent, which means I meet a strategy for the environment. The environment knows how to solve non-determinism in the domain. Well, this is X time complete in D, and is double X time in the assumption. So if the assumptions are small, this is good. And that is X time complete in D is somehow to be expected since D is given in a compact representation and we need to do some checking on the full state space of the domain. And then when we go to the goal, in the case the environment specification is already consistent, so we don't know, we already have checked separately that it's consistent, okay? Then the problem is X-time complete in the domain, is double X-time complete, is double X-time in the assumption, and double X-time complete in the goal. And here there is a hole in this analysis, because we don't know actually if it is 2X-time hard in the assumption. So obviously if you have to check that the assumptions are consistent, it's going to be 2X-time. But assuming that somebody told you that they are consistent, then checking that the planning problem itself, what is the complexity of the planning problem itself, we have only an upper bound of 2X-time. So I'm done. Essentially, we have this idea of environment specification, the specification of environment strategies. Okay, it's very powerful. It solves in a very natural way what is an environment specification, what is an environment assumption, okay, which was very unclear from the literature, not only in planning, but also in synthesis, in formal methods. And the other thing is that actually we can reduce this to techniques that somehow are known, okay? And these techniques have been proposed in formal method, have been proposed also in our community, for example, KR 2018. Now, all this work, I've been using linear time formalism. However, I want to make this point clear. If we're talking about strategies, we are talking about trees, because a strategy is a tree. Given the current history, you do something. So you need a collection of all the possible history. And what you do is non-deterministic, so it's a tree. And instead we are using a linear time formalization, okay? This is why we need somehow to use the logical service of realizability within the definition, because otherwise, really LTL does not have the power to talk about these things. It cannot talk about trees. But there are other logic that talks about trees. There is CTL, there is mu calculus, there is situation calculus, there are a lot of action logic that we have studied in the years that are branching. So I think that the next step is to look at specification of strategies in logic that are different, they are more suitable for talking directly about trees instead of traces. And that's it. Thank you. Let me tell you, I'm hiring. So please talk to me if you are switching position. I have a very big grant, all to be spent in Sapienza. The only thing I can do with this money is to hire people. I'm going to be generous. Talk to me.
Hi, Giuseppe. Thanks for the nice talk. I have a quick question. You mentioned in passing that you assume that the environment assumption is small, and I'm wondering why.
Well, yes, I can be a little bit more precise on this.
Yeah, great.
So we have to be careful of separating difficult environment assumption from easy environment assumption. For example, the domain itself, it's an environment assumption, okay? It's environment specification, it's easy, okay? If you have non-Markovian specification of the domain, I think they are also easy. If you go to LTL, they talk about infinite path, etc., they are going to be difficult because they introduce a difficulty that is the parity automata and the determinization of the parity automata. Unfortunately, is there, and this will make everything not very scalable. So it's important somehow that either these assumptions are specific formulas that we know already how to handle, or if they are completely general, they need to be small, because the kind of computation we need to do on that is going to be hard. It is hard, okay?
So you want it to be small, but it may. I guess my intuition is that it may not be small, and yeah.
Yes, but the point is exactly not to make it monolithic. So don't put everything in the assumption, but try to keep things separate so that you keep the difficult part small, separated from the easier part. Okay, this is my message, not in general, they can be anything else.
No, I don't think we have time for another question. We need to move on. So thank you, Giuseppe.
Thank you.
Can you help me? And then where is it located? Thanks. So today I'll talk to you about learning models that describe behavior. And we are interested in learning models that are human interpretable. That's why we are using linear temporal logic to describe such a behavior. So very quickly, linear temporal logic is this formal language that talks about sequences of states. We have temporal operators, next, until, always, eventually, release, and with next that tells you what happens in the next time step if such time step exists. So linear temporal logic has these temporal operators and also extends propositional logic. We are using LTLF, that is the restriction of LTL, evaluated with semantics on finite sequences of states. So this picture kind of depicts what we want to implement. It's a system that takes as input a set of examples, user behavior, and we want to design this black box that outputs an LTLF formula that is consistent with the set of examples. What does it mean? It means that the positive examples will satisfy the LTLF formula, and none of the negative examples will satisfy the LTLF formula. As usual, this behavior is considered to be a sequence of states, and states are just sets of propositions. Okay, so there exists a bunch of existing related work in which people learn DFAs. And suddenly, recently in the last year, many people have started to learn LTL. LTL interpreted over infinite traces, but somehow with input that is finite traces, so kind of this mixer. I want to highlight this work by Nader and Gabran last year, where they learn exact models, and another piece of work by Shah and Kim that they learn non-exact methods using Bayesian approaches. Okay, so we are using, that's not surprising, alternating automata to check whether a state trace, that is a demonstration of user behavior, satisfies a given LTL formula. So for those that are not familiar with alternating automata, think of it as progression of the LTL formula. And you will understand it better with an example. So imagine, right? So we want to construct an alternating automata. This alternating automaton is a composition of these skeleton structures that we define here. These skeleton structures represent temporal operators, and they are composed in a tree. So if we want to satisfy that, we want to check that an example satisfies alpha and beta in a certain time step, we go to that skeleton in the corner up there, and it tells that we have to check that the example satisfies alpha and beta. If we want to check that an example satisfies alpha or beta, so we go to the other skeleton, and it asks us to check that the example satisfies alpha or beta. Now it gets more complicated. So if we want to check that an example satisfies eventually alpha in a certain time step, this skeleton tells us that we have to choose between checking that the example satisfies alpha or moving to the next time step, that's what this circle says, and looping and recursively check eventually alpha in the next time step. Another one says, you know, what if we want to check next alpha, so we have to move to the next time step and check alpha. And the other one is a little bit more tricky. What if we want to check weak next alpha? So we want to move to the next time step if it exists and check alpha. And this double circle tells that this node is accepting. Okay, so that looks very much like progression of the LTL formula. And now we have these results, right? So a tree expansion is accepting if all the leaf nodes, after we do this tree expansion, are accepting. And we have means to check whether a state trace satisfies phi if this automaton that we construct has an accepting tree expansion. Okay, so with this construction, we are ready to have an algorithm that does passive learning of LTLF from a set of positive and negative examples. We just need to set bounds on the length of the LTL formula. Is the same as the number of skeletons that we will need, and we'll just need to figure it out, the combination of skeletons, so that these three expansions, right, so for the positive examples, there exists a tree expansion that is accepting, and for the negative examples, there's no tree expansion that is accepting. So this is very combinational, and that's why we are using SAT to solve this problem. Recall that SAT is this problem in which we have variables and a formula, and solution is to find an assignment, a truth assignment of variables that satisfies the formula. So now I'll give you very quickly what are the clauses in this reduction to SAT. We are going to have skeletons, S1 to Sn. The skeletons are rooted in S1. And then each skeleton will have to be of one type, right? It has to be associated with a subform, with an operator. This operator can be an and, or, next, with next, etc., or a literal. We have more constraints here. We asked that each skeleton has two subformulas, alpha and beta, and also one literal associated with it, right? And then what we have to do is to enforce for positive examples that there exists a tree expansion that is accepting. So for this, we use some variables that are called run, that are indexes by the example, the time step, and the skeleton. So we start with run E11 for each example, and then we are having clauses that basically simulate these three expansions. So I have some examples here for a subformula alpha and beta. So we imagine that we are progressing, right, this alpha and beta subformula. And we say, well, what happens if we are in this run, ETS, and S happens to be an AND formula, and the alpha subformula is associated with this skeleton S prime. So then this clause says, well, progress this branch in the tree, and then check the run in the same example, the same time step, but in the skeleton S prime that represents the subformula of S. And same for S prime prime that represents beta, that is the other subformula associated with alpha and beta, and so on. Okay, so that gives us a mechanism to check that the skeleton accepts the positive examples. Now what happens with the negative examples? We want to make sure that no tree expansion accepts a negative example, but that's too hard. There's many tree expansions. So instead, we are doing something more clever. We are thinking on the dualization of the alternating automaton. So we are building an alternating automaton that accepts exactly the complement language of the automaton that we want to learn. And then we are asking this second automaton to accept the negative examples. Does it make sense? Okay, so now there's a super nice property, that is, dualizing alternating automata is very, very easy, trivial. All you have to do is to take these skeletons and dualizing them. What does it mean to dualize them? It means that we have to replace ands by ors, untils by releases, next by weak next, and always by eventualis, and the other way around. So there's another nice property, that is that we don't even need to construct a separate automaton. We can simulate the runs on this dual automaton with the skeletons of the original skeleton automaton by just pretending, dualizing them on the fly. So, for example, imagine that we are simulating a run, a tree expansion, in the dual automaton for a negative example that corresponds to an AND operator, to an OR operator. So all we have to do is to pretend that the AND operator is an OR operator and simulate the two branches of the OR. Okay, so now we have means to learn from a set of positive and negative examples. What we also introduced is a way to do active learning. So active learning is about an agent that queries an oracle and can query two different kinds of questions, right, of queries. Membership queries, that is, hey, this is an example. Does it belong to the model that I want to learn? Or equivalence queries that are, hey, this is an LTLF formula that I think is the correct one or not? And then the oracle replies with a counterexample or with an OK if you have learned the formula. Okay, so we analyzed the sample complexity. It turns out that we can learn with an exponential number of carefully defined examples. And that gives us basically exponential savings compared to what happened if we wanted to learn a DFA instead of an LTLF formula. So that's something good. We identified different practical applications of our system. And then we ran experiments to check the interpretability and the scalability of our methods. So we can learn formulas that are very interpretable. Everyone can understand P and Q, weak next P and Q, etc. Whereas if we had to learn a DFA, this DFA would have had a lot of edges, 32 edges that cannot be interpreted by a human. We also tested the scalability of our approaches in learning different classes of formulas. And we found out that we have good performance at learning formulas up to size 8. We can learn them with less than 20 examples and less than 1 second. And then we did a nice experiment in behavior classification where we took the OpenStack's planning domain, we designed 4 different behaviors, and then we ran the top K planner to generate 1,000 plans for each behavior. Now the question is, can we learn LTLF formulas that can distinguish between these different behaviors? And if we can do, how many examples do we have to do to give to the learner? So with 4 examples, 4 positive examples or 4 negative examples for each behavior, we are able to learn formulas that discriminate between different behaviors. And compared to an LSTM model, we can do it much, much faster, 2 orders of magnitude faster, whereas we are also interpretable as opposed to a black box deep learning system. Conclusions. So we presented a novel mechanism to do passive and active learning of interpretable models in LTLF. We exploited the duality in alternating automata to learn more efficiently from negative examples. We exposed how many examples do we need to have, worst case, to learn. And we identified a bunch of applications for which our system is useful. And with this, I conclude the presentation, and thank you very much. I welcome questions.
Thank you, Alberto. You talked about the complexity of the passive learning problem with respect to the number of demonstrations. Could you comment on the complexity with regards to the vocabulary size, like number of APs and also the average length of the traces?
Right. So I don't have the exact numbers in my head, but here's a quick calculation. So imagine that you want to learn a formula of size n. So you will have basically n slots to fill in with something, either an operator or a proposition or a temporal operator. So you have a limited number of things that you can fill in. And how many combinations of formulas do you have? It's going to be exponential in the size of the formula. Now, well, you can count how many. It's going to be linear in the number of propositions, probably, and also linear in the number of temporal operators, probably less than that, because there are many formulas that are not well constructed. Again. So in this talk, I will present joint work with Sheila McIlraith and Meghyn Bienvenu, in which we try to understand much better what's the relationship between AI planning and reactive synthesis. So just to put some context, in the recent years, there's been lots of advances in LTL planning and also in LTL synthesis, and a number of different authors have identified that there are similarities between these two models. So in this paper, what we do is to establish a clear correspondence between AI planning and reactive synthesis. And this is useful because we can establish theoretical results. We can also bring technology from one of these models and apply it to another, and understand in reality what is the strengths and the weaknesses of each model. So let me introduce you first what's reactive synthesis. In reactive synthesis, it's like a game. We have an environment player and a system player. Each one has their own variables. And now the game is a turn-based game. So the environment in each turn selects a subset of variables, and then the system selects a subset of variables. That generates a trace. And the trace is winning if, for the system player, if it satisfies an LTL formula. Now the realizability problem is to decide whether there exists a winning strategy for the system, and the synthesis problem is to actually compute one. As I said, we are using LTL to describe the objective for the environment system, for the system. And now let me switch gears to the other model that I want to present, that is fully observable non-deterministic planning. It's very, very similar, and you will see the similarities very quickly. We still have two players, the environment and the system, but now we have a kind of a different setting. We don't have variables anymore. We have fluents and actions. The environment selects the fluents, which means that the environment selects the state of the world, and the system player selects which actions to take. So as usual, right? So now this is a turn taking, starting in the initial state of the problem. The system has to apply one action at a time that has to satisfy the preconditions in the given state, and then the environment has to react to this action that the system applies with updating the state. And this updating the state has to follow certain rules, the rules of the planning problem. It has to respond to some non-deterministic effect of the model. So now this is like a similar game where now we have an LTL goal for the system player too, and the objective for the system player is to compute a strategy so that all executions satisfy the LTL formula. Okay, so now we have kind of a picture that LTL synthesis and font planning with LTL goals are kind of similar. So, but still we don't have all the ingredients to fill in the gap. What we need here is another model that is called structured games. So structured games merge things that are common in LTL synthesis and in planning too. So as usual, it's a two-player game with environment and the system. We have X variables controlled by the environment, Y variables controlled by the system. But now we have lots of structure. We have a formula theta E that describes the initial move of the environment. That looks like the initial state in a planning problem. We have a formula theta S that describes the initial move of the system. And now we have formulas psi E that describes how the environment can react according to the previous state of the game. That looks like state, the effects of an action. And then we have a formula psi S that tells how the system can act according to what was in the previous state and what's the current move of the environment. And of course, we have an LTL formula, phi goal, that describes the objective of the system. So the dynamics of this game is as follows, right? So the environment and the system make moves until someone violates the rules. If someone violates the rules, then loses the game. But if both players are playing according to the rules, then the objective is for the system player to satisfy the formula. There's a nice theorem here that actually is very, very important that says, well, you can now reduce a game structure to a regular synthesis specification. And it goes as follows. So we have, what it says here is, if the environment player makes the first move as it should, then I want the system player to make the first move as it should, and always behave according to the rules until the environment player fails to follow the rules. But if it's the case that the environment player follows always the rules, then I want the system player to satisfy phi g. Okay, so now we can fill in the gap, and we have a much clearer picture of these three models. And we will have a much clearer connection in the next slides of how to map one thing into another. But there's a mapping from LTL specifications and game structures that we already know how to do. That is according to the last theorem. And LTL specifications in particular can be seen as game structures without a structure. Okay, so in one of the big contributions of our paper is to establish a clear mapping between LTL font and game structures. And I will not cover all the two directions, but I will do only one. That is the reductions from LTL font to game structures. So as you have maybe the intuition that, you know, a game structure looks like a planning problem, and it does. So the reduction, all it has to do is to map the fluents, you know, establish the x variables to be the fluents, the y variables to be the actions, theta e to be a formula that corresponds to the initial state of the problem, and then set the rules of the system player to be, you know, apply just one action at a time and respect the action preconditions. And then the rules for the environment player are that the reaction to a move of the system has to be an update in the state that respects the effects of the actions. It's actually very, very simple. But what helps us, this formula, is to establish complexity results. Before going to the complexity results to font planning, I have to just cover very quickly the complexity results that are already known for game structures. So it basically says that a game structure can be solved in double exponential time in the size of the formula and in polynomial time in the size of the search space. So there's a clear, these are clearly decoupled, right? That's actually very useful. So now, because there's such a clear correspondence between font planning and game structures, we can expect this to have the same complexity results, and in fact we do. There's exactly the same result for font planning. Font planning with LTL goals is double exponential in the size of the goal formula and polynomial in the size of the search space. Also similar results, or if not the same, for LTLF font planning. Okay, so having these complexity results that font planning with LTL goals is double exponentially hard in the size of the goal formula, it's kind of like too much, right? So what we wanted to find is whether there was a fragment of LTL and LTLF for which we could do planning with tighter complexity bounds. And actually, we found two fragments, GR1 for LTL formulas and PDDL3 temporal operators. For those fragments, we can do planning in exponential time. So GR1, for those that don't know about it, are formulas in a specific syntactic form that says, it's a conjunction of always eventualities implies a big conjunction of always eventualities. Even though this might seem very, very restricted, it has been shown that many industrial patterns, through some massaging, can be transformed into game structures with a goal of this form. So same thing will apply to planning. Now we have a theorem that is already well known that says that game structures with GR1 goals can be solved in exponential time in the number of variables that appear in the GR1 formula. So can we expect the same result to appear in planning? Yes. So we have a similar result in planning that says that font planning with GR1 goals can be solved in exponential time and with a domain fixed polynomial time in the size of the goal formula. Okay, so now let's move to the finite world, LTLF font. So can we have the same results that we had with GR1 goals in LTLF? Yes, we can, but sadly, GR1 formulas, when interpreted over finite traces, they don't have any meaning at all. They reduce to final state goals. So is there any other fragment of LTLF that is interesting? We found PDDL3, right? PDDL3 is a standard. It has some temporal operators that basically reduce to font, to LTLF formulas. We can transform these LTLF formulas into deterministic finite state automata that have fixed size, except for some PDDL3 temporal operators that have some parameter n. And in this case, the size of the DFA is linear in those parameters. Theorem. So, well, what we found is that you can reduce this font planning with PDDL3 goals into a parity game over automata, and because these automata, these DFAs have bounded size, everything is somehow bounded. So if it happens that if you bound the number of PDDL3 temporal operators that appear in your goal formula, and you also bound these n parameters that appear here, solving font planning with PDDL3 goals is also X time complete. So this is actually a good result because we know that font planning with final state goals is X time complete. And we have found two fragments of goals, GR1 and PDDL3, that are richer than final state goals, but for which we fall in the same complexity task, complexity class, sorry. So in summary, we established a bidirectional mapping between AI planning and font planning with LTL and LTLF goals. The reduction preserves structure and decouples the goal from the domain. We derived known and also novel complexity results, and we found two interesting fragments of goals for which we can do planning in X time. For future work, we plan to extend these results to other formal languages and incorporate environment assumptions and partial observability into this model. Thank you very much. With this, I conclude my talk, and I welcome.
Well, personally, I'm really not familiar with LTL planning at all, but the thing that came to my mind is, if you can convert these between those different formalism, then can you use LTL font planner to solve the other side to actually?
That's a very interesting question. Yes. So we, under my experience, right? So LTL synthesis doesn't have any structure, so everything is a single formula. But now the synthesis community, through competitions, have started to move more into a structured way of looking at LTL synthesis. So they have the equivalent of the PDDL for them That includes formulas that describe initial state, that describe constraints on the environment, environment assumptions, constraints on the system, and so on. So to respond to your question, right, as long as they are moving to a more structured way of looking at synthesis, I think that we can bring planning technology to solve their kind of problems. And the fact that we have formulas here that decouple the goal complexity from the domain complexity, we are very hopeful, and it also aligns with what Giuseppe also said in the previous talk, that we think that there must be ways in which we can exploit the structure of the transition system and decouple it from the goal. So yeah, I think that maybe planning technology can be used to exploit this structure. Thanks.
Here.
Yeah. So the University of Toronto is also hiring. So for those of you that are completing the PhD or are even more senior, talk to Sheila. Yes, please do.
Okay. Yeah, it's on, right? Okay. All right. Thanks. Okay. I can't even see what I'm pointing at. All right, so this talk is going to be very different. There's not going to be any LTL in it. My apologies. So I'm going to tell you about replanning for situated robots. And as you can see, we have a lot of authors, a few of whom are here. And so let me motivate replanning by a true story from ICAPS last year, where we had this paper by the same people, Planning While the Clock Ticks. So this paper is a follow-up, and we had a plan, right? The plan was for me to give this talk at ICAPS 2018 in Delft. And as you can see by this lovely Photoshop that I had to do to put my face in there, that didn't happen because an unexpected event occurred. My son was born a month early, and so instead of me giving the talk, I was there, and Andrew gave the talk. And by the way, Andrew isn't here now because they're expecting their first baby, so I don't know what's going to happen next year. So in general, we are concerned with the problem of a situated agent, and if you're me, you're thinking of a robot, but you could think of a virtual situated agent. And so the agent is acting in some temporal planning problem. So we've got the usual fluence, derivative actions, initial state. We've got timed initial literals because, as I'll say in a second, we want to actually have deadlines or temporal constraints and a goal. And the agent is in the middle of executing some plan or schedule pi. And then something triggers replanning, right? Maybe the robot had a baby, or maybe something unexpected happened, maybe it got a new goal. We're not really concerned with why replanning was triggered, but we need to replan. And so what we need to do is to find a new plan pi prime, such that if it takes us d time units to find this new plan, we will be able to execute pi prime at time t plus d. And so the reason that time is important here, right, is because of these timed initial literals. So you can think of them as expressing something like the bus comes at 10 o'clock, right? So I need to be done planning in time to start executing the plan to catch the bus, right? Okay. So this is the basic premise of situated temporal planning, and in the case of replanning, there's another complication that happens because you are already in the middle of executing some action, right? And that way, and for this, we're going to consider two different cases, right? So we're going to look at the case where actions are non-interruptible, and we're going to look at the case where actions are interruptible. So to explain that, let's look at this very simple durative action, right? So we've got a start condition of being at A. We've got a start effect of not being at A. We've got an end effect of being at B. So this is basically the standard way of modeling a durative action that goes from A to B, right? And it's got some duration. And so let me ask you this. Does this PDDL model describe a ballistic launch? Right, so we put the object on some catapult at A, and then we launch it, and then it reaches B? Or does it describe driving from A to B? So it can describe both, right? Because PDDL just tells us what happens at the start, what happens at the end. It doesn't actually tell us what happens if we want to interrupt the action, right? So this is one of the challenges that we're going to need to handle in this paper. And so we need to know when we can set the duration or change the duration or maybe even interrupt the action or something like that. So before I get into that, I'm going to tell you about how we handle the case where actions are non-interruptible. And it turns out that when actions are non-interruptible, it's really a simple reduction to the situated temporal planning paper that we presented last year. So, right, so think of all move actions being ballistic launches, right? And then what we can do is create a temporal planning problem, a situated temporal planning problem, which basically describes the currently executing actions. So you can think of it as having like a dynamic initial state. So we have the current state, but when the currently executing action A ends, and we know when that will happen, then its effects will happen. And furthermore, we should probably not violate its invariant condition because otherwise, PDDL doesn't tell us what will happen, but presumably something bad. So this is basically what we do. So there is a bit more detail here, right? But basically we add a fact EA that tells us that action A has ended, and we encode tills that tell us that when the action ends, then EA will trigger and its effects will happen. And we make sure not to violate the invariant conditions using this. The full details are basically here, but in the paper they're in a bit more detail. Okay. So this is the easy case. What happens when we have interruptible actions, right? When we have interruptible actions, we don't even know how we can interrupt the actions, right? And so what we did here is we invented this idea of something we called bailout action generator. And you can think of a bailout action generator as kind of a local version of a black box successor generator. Okay, so it's something that you call and you say, hey, this action is executing here. What are my options for bailing out of this action? And it's not described symbolically, right? It's implemented in code. But it's not like we have to describe the entire problem using a black box formalism, right? So the thing is that this is local. So we only need to describe how we bail out of driving, how we bail out of paragliding. I don't know, right? Choose any action you want. You can describe different ways of bailing out of it. So paragliding is probably not a good example, but who knows? Okay, so the bailout action generator basically produces a set of durative actions, right? So the output is a set of durative actions that our situated temporal planner can then use, right? So easy, but there is a further complication. So let's look at this very simple example. So we've got this little fancy robot, and it's driving from A to B, okay? And we want to bail out, right? So one option is to change the velocity. Changing the velocity corresponds to basically changing the duration constraint, and that's actually fairly easy to do. Okay. Another possible bailout action is deciding to drive to C instead of to B, right? So maybe we've got a Mars rover, right? We heard about these. And so I'm driving to B to drill some rock sample or something, and then suddenly I realize that my drill is actually broken, right? So there's no point in actually going to B. I want to bail out of this drive. But if I model this drive as a derivative action, there's no way to do that, right? So our bailout action generator will say, okay, so you can go to C instead, right? Change the destination. So let's look at how long this bailout will take. So the blue line is how long it will take us to drive to see how long the bailout action will take, right? What is the duration of the bailout action as a function of when I bail out, right? So if I bail out kind of here at the closest point to C, then it takes the shortest amount of time. If I bail out after one time unit, right, one time unit after leaving A, it'll take longer. If I bail out after I pass the closest point, it will also take longer. So this is not monotonic. And this is not something that we can really deal with. Okay, so the bailout action has a time-dependent duration, right? The duration of the bailout action depends on when I start it. And that's not actually something that we can model in PDDL, or at least not easily. But fortunately, we had Andrew on the team. And Andrew said, well, the duration of the bailout action is non-monotonic, but the time you reach C is monotonic, okay? So basically, if I'm driving to A to B, and I decide to drive to C instead, the earlier I make the decision, the earlier I'll reach C, okay? So this is kind of the length of the delta, right? But the time I'll actually reach C is monotonic. And so we can use that monotonicity and do some efficient temporal reasoning. So let's talk about why we expect to have this monotonicity, right? So if you think about this bailout action generator, you can think of it as really solving a planning problem at a higher fidelity model of the world, right? So maybe our PDDL planning plans at the level of waypoints, and our bailout action generator plans at the level of an RRT or something like that, right? In the continuous space. So if a bailout action is really an optimal solution to this higher fidelity planning problem, then we can easily prove that we get monotonicity, right? It basically means that if bailing out earlier is slower, then I'll just bail out earlier and follow the original plan that I had and bail out later, right? So getting this monotonicity, assuming that your bailout actions optimally solve this higher fidelity planning problem is a good exercise for students. What took us a bit longer was to realize that even if we don't have this optimality, right, because if you've ever called a motion planner, it's not optimal. But we can do some post-processing and get this monotonicity. So assuming now that we have kind of a discrete number of points where we can bail out, we can basically do some post-processing and check that if the motion planner that we call to bail out from, let's say, the first point takes longer than the motion planner we get from the second point, then we can just continue until the second point and do that, right? So we can basically do this optimality trick, but with this limited set of discrete options we have, and we get this monotonicity. Okay, so that's all well and good, but we still have a temporal planner that needs to reason about these actions with time-dependent durations. Okay, so we used Optic, and Optic uses, for lack of a better word, an STN. It's not really an STN, but let's go with that. So each search node that Optic generates has a simple temporal network that describes the temporal constraints between the actions and the plan. And when these actions have time-dependent durations, then we can't really use an STN anymore. But again, fortunately, we had Andrew. And so Andrew came up with this algorithm that can still do efficient temporal consistency checking with monotonic time-dependent durations. Okay, so it only works because we have this monotonicity. The basic idea, so the full details are here, but I'll just try to explain the basic idea without going into the details. So the basic idea is that we have a relaxed STN, and that's a real STN, okay, without any time-dependent durations, by looking at the global minimum duration and the global maximum duration of each activity, okay? And then we solve this STN and we get the earliest schedule that we can. If that's feasible, great, right? If it's feasible with the real time-dependent durations, then we're happy. If it's not, then we basically tighten the durations of all the actions that we have according to the schedule we got. And if we didn't have monotonicity, we would actually have to do some sort of backtracking here. But because of the monotonicity, then this is fine, and it converges to checking whether this is consistent or not. Okay. So let me tell you about the empirical evaluation that we did. So we basically had to compare to something. And we didn't really have anything to compare with because nobody actually did this before. And so we came up with something that's rather naive, but it's basically just using the situated temporal planner that we came up with last year when the currently executing actions finish. So we can still plan while the action is executing, but we're constrained not to start executing anything until the state has settled down into something that's really static, right? And what we do is we compare goal achievement time, which is planning time plus plan makes span. So basically when we will achieve the goal. That's why it's called goal achievement time. So we did this on two benchmarks. One is the RoboCup Logistics League, which is concerned with robots driving around in a factory and trying to manufacture different things. And then the other one is a turtlebot doing office delivery, which we actually integrated with ROSPlan. And then, so this was a robotics track paper, and one of the viewers said, oh, this is pure planning. So, okay. So on the RoboCup Logistics League challenge, we had problems with 1 robot, 2 robots, and 3 robots. With 1 robot, our approach didn't actually do anything better than the baseline, because when you only have 1 robot, then there's really no benefit from doing things earlier than when the currently executing action finishes, because you only have 1 action executing at a time. So with 1 robot, we gain nothing. We actually lose a little because the planning problem we solve is more complicated. With 2 robots and even more with 3 robots, then our approach, which is R, does better than the baseline. Still solves less problems, but the problems it does solve have a better goal achievement time. On the second benchmark, we've got this turtlebot delivering coffee, and we could use some of those here. And so we had 2 different sets of problems. In this set, there was only 1 type of bailout available, which is bailout to the dock. And in this one, our approach was able to solve all of these problems, and the baseline was not able to solve anything in time, so we had tight deadlines. And then in the second set of problems, there was the option to bail out to the dock or to some other charging stations around. And so again, our approach solved everything, and the baseline only solved 2 out of 5. And so in conclusion, we presented an approach that breaks a little bit of the domain model abstraction barrier by using these bailout action generators, kind of local higher fidelity black box models. And we saw that using this and handling situated replanning requires us to handle time-dependent durations. We saw the benefit, especially in cases with tight deadlines and multiple agents. And we're kind of working on blurring the line between, planning and execution. I know Malik has worked a lot on that before, and others. Okay, so thank you. Questions?
Hello. So I was wondering if you really need this machinery of bailout actions, you could maybe just, given that you replan from time t, you could just kind of define local temporal actions that you are only allowed to start at time 0 or your current time.
So I mean, that's something that the bailout action generator can tell you, right? But we can't really say that for any given type of situation, that's the right thing to do. So it's certainly true that there are probably many examples where you can do that and not actually need a bailout action generator. But in some cases, you might need it.
So the bigger contribution to me seems to be this idea of having a variable duration, which is somewhat orthogonal no, to the idea of interrupting action.
Yes.
You could have that
Yes,
even without interruption. No?
Yes, that's true.
Any other questions?
Why don't you generate a waypoint rather than an action? If you said, I'm stopped at D, I create another object.
Yeah.
And if your drive is anyway lifted from A, B, C, D, wherever, then your path planning will say from D, I can get to C, B, or wherever in this amount of time.
So, I mean, this is really what the bailout action generator does, right? But, I mean, so in the PDDL model, waypoints are objects. And we don't really have PDDL actions that can generate objects as an effect. Plus, we don't really know where to put the waypoint in advance.
Put the waypoint where you decided that you don't want to execute the plan any further, no?
So that's part of the planner's decision. The planner, when it replans, so I can start replanning now, and I can decide to bail out here, or I can decide to bail out here, or I can decide to bail out here, right? So that's the planner's decision when it's replanning. So we need to put multiple waypoints.
But if you put one waypoint and the path planning would tell you anyway, you should continue a few steps forward and then you turn.
Yeah,
you get the same.
That's the optimality that I talked about, yeah.
All right.
All right.
Thank you, Erez.
Thanks.
Thanks, Erez. Sorry? I'm using this one. Okay, thank you. So before pizzas arrive, so this is a short paper in collaboration with colleagues from Freiburg, ANU, and King's College. I have to say that the main contributor and the main author of this work is Alex Heinz, but he couldn't make it, ICAPS, so I'm presenting it, but most credits go to Alex. So the idea of this paper is to explore the use of model checking for temporal planning, following the paradigm of planning as model checking. And I want to start by saying that this line of work was originated by Paolo and some other friends, so pay homage to Paolo. But there is a history of using model checking for planning based on the observation that the two problems are actually very related, because on planning you have a description of initial and goal state and the actions you can have, and the goal is to find a plan from the initial state to the goal. And in model checking, you have a formal description of your systems and a property you want to verify, so you try to explore the state space and check if there is a state that violates the property. And in this case, you return an error trace that can be seen as the plan that you're looking for in planning. So there is really a close synergy between the two problems. And recently also there was, well, a few years ago actually, a Dutch seminar on planning and model checking, and you might recognize some faces. I guess it's time to do another round probably of this event. Now the focus on this paper built on some previous work where some of the authors, we basically translated PDDL plus problems into model checking for hybrid systems. And the idea there is that this is the description from Maria and Derek on describing the semantics of PDDL plus. And this is a standard hybrid automaton. The difference and the problem there was that in PDDL plus, all transitions for processing events are mass transitions, meaning you need to move between states when a process is triggered. While in hybrid automata, transitions are may transition. You may or may not take the transition. And we address that problem using over-approximation, so allowing more behavior. And this was very helpful in proving unsolvability of PDDL plus problems. Then from here, we wanted to consider temporal planning instead. So from PDDL plus into PDDL 2.1 planning. And for this, using hybrid automata would have been overkilling. So the idea was to try to use timed automata instead. And instead of using over-approximation, here we use under-approximation. I'm going to explain this in a minute. So we looked at the MICTA directed model checker. So in directed model checking, rather than trying to explore all the states, you try to drive the search in order to spot and to find as soon as possible the error states, if there is one. And this is a tool developed by Martin and Sebastian Kapper-Smith. They use some basically heuristic guidance in order to drive the verification search to spot the error trace. That's the idea of MICTA. The framework of timed automata, just for those of you who are not familiar with this, the idea is that they allow to model continuous time using what are called clocks that model linear continuous time. So that's an example, for example, using a light. So you are in state L0. If you press the button, you move into L1, and the clock, X in this case, starts running. So the timed automata allows you to count the linear progression of time. Now, what we did in the paper is that we basically translated all the main components of a PDDL 2.1 model into the corresponding timed automata representation. In the paper, there are the details. I'm just going to show you something which is, was a bit tricky, which is how to model the epsilon separation in PDDL 2.1, which means in PDDL 2.1, interfering actions cannot start or end at the same time. So we use these, the semantics uses this epsilon separation. And the idea there is that you start in the first location, then you move into a location where you stay for epsilon units of time, and during that time, you lock the execution of any other automaton. In this way, you prevent two interfering actions to be executed at the same time. Now, the main issue, also from a computational point of view, is that the complexity of timed automata increases with the number of clocks. And in the current translation, we would have basically one clock for each grounded action, which is computationally quite expensive. So we had to come up with some solution to mitigate the explosion in the number of clocks. And so what we did was basically to come up with this dynamic encoding refinement. And the idea is the following. I'll just give you, I'll give you an idea, then the details are in the paper. Actions that should not be applied in parallel, they can share the same clock, because you don't need to separate clocks if those actions are not executed in parallel. So something that we could do is to basically follow a bucket-based encoding, where the idea is that you use buckets where you put all the actions that don't need to be executed in parallel. And they can share clocks, so in this way you reduce the number of clocks. It's an under-approximation, as I mentioned, because in this case you are preventing some behaviors to be allowed. So you are considering less behavior than possible. The idea of the refinement is that you start with a very strong assumption, meaning only one bucket, meaning there is no parallelism at all. And then you start refining if no solution is found, meaning that you split at least one bucket into more than one bucket. And in this case, you start adding clocks, which means adding the possibility of executing in parallel more actions. Clearly, the main questions are how to refine and when to refine. And I guess this is why this is still a short paper rather than a long paper, because we are, working on how to make better improvements. We have a few procedures described in the paper. One is to identify pairs of actions where the start effect of one action supports the invariant of another action. Clearly, if this is the case, you need to be able to run these two actions in parallel. And this is one criteria we use for deciding when to split one bucket into more buckets. Again, the formal procedures are described in the paper. Some experiments, so we compared this approach with a number of temporal planners in a number of domains from the IPC. I guess what the experiments say is that there is, good coverage with strong performance in a couple of domains. So, I think the main message is that these results suggest that model checking can still help planning, and in particular temporal planning. Also with the idea that we will be able to, to leverage all the progress that will be made in model checking. So I guess the main message here, we should look in an optimistic way at the possible synergy between planning and model checking, also in temporal planning. A few things we have in mind. As I said, we want to specify more sophisticated strategy for the refinement, for how and when to refine. Consider under approximation also on a number of automata. This was done in classical planning from Basel, and the idea is to explore the same also for temporal planning. Then we would like to adapt one of the heuristics that MICTA is using, which is PDB, also for PDDL 2.1. And finally, MICTA is just one instantiation of the framework, but also other temporal model checkers could be used for trying to use this translation. I'm done, and I guess we are all starving, so buon appetito and thank you.
Hi, thanks for the talk. I think there are some compilations of temporal planning with limited concurrency to classical planning. Do you think this approach could be combined with that as well?
That's a good question. I think, yes, we could. We should explore that. I guess the point here, we want to try to leverage the capability of temporal reasoning in those model checkers. But in order to, to increase scalability, definitely we can explore that. Thanks. Time for pizza. Thank you.